Okay, now we're going to look at some chord properties of a circle. So first, one of the things that we're going to have to remember is how to measure the distance between a point and a line. When you want to measure the distance between 2 points, that's pretty easy. You know exactly where to go. But when measuring the distance from a point to a line, there's infinite points on that line. So like, do I go to the red point? Or do I go to the green point? Well, actually, let me make that a little... Do I go to the green point? If I measure those distances, the green distance and the red distance are not the same, right? So how do you know which point to go to? Well, really, you're going to the purple point. It's always the shortest distance from the point that's not on the line to the line. Another way to say that is you want to go perpendicular. There's only one point that when you measure the distance or make the segment, there's only one point on the line so that that segment makes 90 degrees with the line. So that's how you measure the distance between a point and a line. We're going to use that later today in this video. All right, so our first property, we'll call these properties, not conjectures. You can pause and write this down. If two chords in a circle are congruent, then they determine two central angles that are congruent. So if I know the lengths of those chords are congruent, then I know these angles here are congruent, the central angles that intersect those chords. Notice these central angles, this red one, the angle goes out to the endpoints of the chord. And let's do this blue one, this blue angle here. Notice that its edges or its sides go out to the blue endpoints. And if those two chords are congruent, the red chord and the blue chord, then those angles have to be congruent. So for instance, if I know that this chord is 10 centimeters and I know that this chord is 10 centimeters, and let's say I know that this angle here is 85 degrees, you can now find x. You could say it's also 85 degrees because of this property. Let's look at why that works, or just kind of show you give you a visual of how that works. So I made a circle here, and we've got this chord that has a length of 5.19 units, right? And its angle measure, I've measured the angle there, the central angle is 60.72 degrees. When I move this, if I move this anywhere in the circle, I'm just rotating it, you can see that the chord stays congruent because the circle has infinitely many degrees of rotation that it stays symmetrical. So anywhere on this circle, I have the chord that's the same length. So I'll put it there. Now, if we draw in the central angle formed from that chord and measure it, we can see it's the same measurement. It's the same degrees. So any chord, and again, it's because of that symmetry, right? There's rotational symmetry here in a circle, and it has 360 degrees. Like I can stop it at any single degree, anywhere I want. So that's kind of what I think of, this symmetry there. So if I have the chords that are the same, then those angles are the same. Even if I change the length of the chord, you can see it sort of adjusting, as long as the chords stay congruent. All right, so that's a visual representation of what we just talked about. Now, because of that property, this next one is kind of easy to come up with. So if these two chords are congruent, because of what we just learned, those angles are congruent. And we know that these are central angles, and so the arc they intercept will be the same measurement. So now the arc, now we're talking about the arc. Those arcs are congruent. For instance, if the measure of this chord was 10 centimeters, by the property we just figured out above, we could say, like, if this angle was 100 degrees, then this angle is 100 degrees. Then from the other day with central angles and their arcs, if I know the angle is 100 degrees, then I know the arc is 100 degrees. So this is saying if two chords in a circle are congruent, then their arcs are congruent. Actually, I don't think I need an apostrophe there. then their arcs are congruent. So a more simplified picture would look like this. If I've got a congruent chord and a congruent chord, and I know this arc is 58 degrees, then I know this arc is also 58 degrees. Or I could find x, if x was that arc. The perpendicular from the center of a circle to a chord is a chord. We're going to skip that one for a second. Let's do two congruent chords in a circle are equidistant from the center of the circle. Again, these aren't conjectures. Properties, call them. Two congruent chords in a circle are equidistant from the center of the circle. Equidistant means same distance. Here's where we have to use that from the warm-up. If you want to measure the distance from a chord to the center, you draw the perpendicular segment. This segment represents the distance to the center from the chord. This is your chord. Right? So that distance, that red segment, will be the same as this green distance over here. The green chord will be the same distance to the center as the red chord if they are congruent. So if this chord is 15 feet long and the red chord is also 15 feet long, then their distance to the center will be the same. Let's take a look at that one. Right, so here I have a chord that measures 5.29 units in length. I measured the distance. I made it perpendicular to the center. I measured the distance to be 3.32 units. So now if I translate or rotate, rotate that chord somewhere else around the circle, you can see that it still has the same length. Even if I change this one, it keeps the same length. Now I want to check the distance. What is the distance? Is it the same? It is. It says that distance is 3.36 units, which was the same as the other distance. What if I make the chord longer and bring it closer to the center? Their distance stays the same, right? So again, it's mostly because of that rotational symmetry. That's what I'd like you to visualize. Okay? And then the last thing kind of combines both of these. So the perpendicular from the center of both of these properties. The perpendicular from the center of a circle to a chord is the bisector of the chord. So if I have a line going through the center so that it is also perpendicular, so two conditions are met. Passes through center, that's met. Two, this is the if part. It's perpendicular for the chord. That condition's met. Then I can conclude, I'll do that in green. Then I conclude that it's the bisector of the chord. So I can conclude that those two segments are congruent. If that's 5 centimeters, then that's 5 centimeters. If the first two conditions are met, you can tell by inspection that it passes through the center just by looking at it. That's condition 1. In condition 2, I have to tell you that it's perpendicular to the chord. If those two things happen, then I can conclude that those two segments are equal because it's bisected the chord. Okay, in fact, these three conditions, if any two of them are met, the third one can be concluded. So I've got this bisector idea, the perpendicular idea, and then it passes through the center. So I can use them in any combination. If I know two of them, the third one must hold. That's what this other conjecture, or I'm sorry, we're calling them properties, is about. It's really the same thing. The perpendicular bisector of a chord passes through the center of the circle. So again, there's two conditions to be met, right? Number one, it's the bisector of the chord. That would be that those two are congruent. That condition is met. Condition 2 is met. That means that it's perpendicular to the chord. And then you can conclude the third one that says it must pass through the center if those two are met. Again, you want to, and so you can see that it passes through the center. This is not our homework, by the way, down here. Just ignore this stuff. So again, those are the same three conditions from before. They're just in a different order. So I want you to kind of think of those three. You got to know those three things about a chord. The bisector of if the line bisects the chord, if it's perpendicular to the chord, then it passes through the center. Or I can choose another two. If I knew it was perpendicular to the chord and it passes through the center, then it must bisect the chord. Or if I knew it was the bisector of the chord and it passes through the center, then it must be perpendicular. Here, let's look at, this is the last thing we're going to do. Let's look at, I'm going to just make some of these things. So let's make a chord. I'll put a point outside the circle. I'll make a line that's perpendicular to the chord and passes through that point. So look, this line is perpendicular to the chord. So no matter where I move it, it stays perpendicular. I need to make two conditions meet. So I have perpendicular, that's 1. If I make it pass through the center and I stop there, that's condition 2. So the third condition says that it must pass through the midpoint of the chord. So let's make a point there. That must be the center of the chord, or sorry, the midpoint of the chord. So it bisects the chord. So let's look at that again. As I move this around, as long as if it doesn't pass through the center, it is not at the midpoint of the chord. But as soon as it passes through the center, it becomes the midpoint of the chord. How can we check that? I can make the midpoint on this chord. So we're going to say, let's see, midpoint of that chord. There it is. That point is right in the middle. So once I line it up on the center, it's on the midpoint. So there's two conditions met. The third is met. Let's look at another one. Let's say I put any old point on the chord here, and I make a line to that point and another point. So if I put that, here's one condition's met, that I'm bisecting the chord, right? This line bisects the chord. The other condition would be, we want to measure that angle, that I make it perpendicular. So currently it is not perpendicular, but if it's bisecting the chord, this line, but it's not perpendicular. Once it meets that second criteria and becomes perpendicular, get it close enough, it passes through the center of the circle. When it's not perpendicular, it's not passing through the center. So that's what you want to remember. Those three properties here, or these three characteristics, if any two hold, the third must hold.